Now we're going to pick up from where we left off in our last lecture, talking about the dipole approximation for transitions in a given atom. And we're going to use that to talk about what transitions are permitted. Now, in order for a transition to be a permitted transition, it means that its dipole has to be non-zero. And so we can consider what wave functions in the initial and the final state actually allow for a non-zero dipole. And so that's what we're going to work through in this lecture here. So let me share my screen and we'll bring it up. Okay, so what we want to think about is when permitted transitions occur when the dipole is not equal to zero. Now, that happens if you consider that the dipole term is equal to the electron charge times the RFI radius. That has to be not equal to zero for a transition to occur. So recalling that the R is equal to RFI is equal to the integral from 0 to infinity, surface of the complex conjugate of the final wave function times the position vector times the initial wave function integrated over the volume. If we consider hydrogenic wave functions. Now remember, hydrogenic is a single electron orbiting around a nucleus. So if we consider hydrogenic functions, such that, for example, psi I, we decomposed it in our lectures about atomic structure into a radial distribution function and then a spherical harmonic function, which was related to the quantum numbers L and M, the function of theta and phi, where Y, L, M, theta and phi was given by 2L plus 1 over 4 pi L minus M factorial over L plus M factorial PLM cos theta e to the I m phi. Now remember, this is the same type of wave function that we defined in our discussion about atomic structure, where we talked about the wave functions for a hydrogenic atom, and we even visualized them in our in-class time. So to be non-zero, so for RFI to not equal zero, it places some constraints on the actual quantum numbers. So for RFI to be non-zero, if we do the substitution of these terms, we get something that goes approximately as the integral of RF of R, Ri of R, the radial functions, R squared dr, times something that's the integral of final spherical harmonic cos theta and the spherical harmonic of the initial state, which is both of those are functions of theta and phi. So from this, we are able to judge that in order to have RFI be not zero, it sets some limits on L and M. So for non-zero RFI, it requires that, pardon me, that the quantum number L in the final state has to be equal to the quantum number of L in the initial state plus or minus 1. That is to say that you have to change the spherical harmonic so that it doesn't integrate to 0. Now, you also want to have that the final M is equal to the initial M. You don't want to change it in all directions. And so this tells us that delta L has to be equal to L, has to be equal to plus or minus 1. And delta M has to be equal to 0. It can also actually be equal to plus or minus 1. That is allowed and will produce a radial function which is non-zero. So this is set up what are called the selection rules. So these are selection rules. Actually, let's write that in another color. Selection rules for hydrogenic atoms. And the selection rules for hydrogenic atoms, I find to be quite amazing that they fall out directly from quantum mechanical descriptions of the wave function for an atom, that these things break down in such a way that you can define what quantum numbers are allowed, produce allowed transitions very easily. So from there, you can then move on back to our description of the various levels and states of atoms and consider which transitions would be allowed, which ones are not. And for example, you can see here that delta L has to be equal to plus or minus 1. That means that you could not go from a P state to another P state. You would have to change from a P to an S or a D to a S. So these are requirements on the angular momentum quantum number, which sets out the selection rules. So also for a single atom, other selection rules are that one, this is again for a single atom, a single electron, I should say, sorry, that parity must change. And that is that if you reflect all coordinates, that the integral would go to 0 for the radial term. And that would mean that you would have no longer a dipole term. So we do require that we have parity changing for our electrons. The configurations of L must change by at least one orbital. And there are no transitions between states of the same config. Now that's just another way of stating that delta L has to be equal to plus or minus 1. In fact, for a 1 electron, the config must change by precisely 1. And this is also known as the one electron jump rule. And finally, the spin cannot change. Which is to say that delta S has to be equal to 0. Now, delta S, the spin cannot change for an electron in this situation for an allowed transition. So these are the rules for a single electron situation in allowed transitions. In our next lecture, we'll move on to the selection rules for the many electron systems, and then we'll put those into a little bit of practice.